Cauchy Euler equation. Cauchy Euler equation. This equation, which is what's stated here, the Cauchy Euler equation, looks very similar to the previous differential equation of nth order. Here we have coefficients a sub n minus 1, and so on, but we have something else associated in the differential equation. We have these polynomial terms, x to the n minus 1, and so on. What this problem or this differential equation suggests is that if you have a differential equation that's linear of nth degree, where you have n derivatives, and so associated with each derivative, there is a polynomial term of that same order. Well, this is x to the n. That's just x to the nth power. It's not a derivative. But if it's associated with the number of the power for the x term, lines up with the order of the derivative per term. If that's the case, then we say that this is the Cauchy Euler differential equation, of which we have a known solution pattern. That's what we'll talk about today. You expect differential equations to be of several forms. You would expect this. I will argue this point for 5 seconds, that this type of differential equation is perfect. It is not the case normally in nature. What am I saying? It is not the case normally that the derivative, like the nth derivative of y with respect to x, matches up perfectly with an x term raised to the same power of the derivative order, and so on. I mean, it's the same way as you go down. You take the third derivative, they're saying that you got to have x to the third times y triple prime. Well, and it's perfect. If you got y double prime, then you got to also have x squared. If you got y prime, you got to have associated with that times x. I mean, that's perfect. That's like the ideal situation. So normally it does not happen. If it does happen, then we solve it like this. Now, what if it doesn't happen? Well, that's chapter 6. In chapter 6, we will focus primarily on differential equations that they can look any kind of way that they want to look based on what happens in nature, which is probably what will happen anyway. You'll get some stuff that you'll say, we never solved that before in class. Well, so if you never solved it before, does that mean that you cannot solve it? Well, we'll give you a method in chapter 6 where we'll say, even if you haven't seen it before, use this method and you can solve it. So that method in chapter 6 kind of goes off the book, off the grid, and we give you a method of solution that is somewhat tedious, but you can find the solution to almost any type of differential equation. But here in chapters 1, 2, 3, 4, and 5, we deal with the so-called ideal situations. So this is a fundamental concept, and so from this we can build on so much hereafter. So how do we solve this guy? Well, here's what we do. And the objective today, to solve the second order Cauchy Euler differential equation. It was another name associated with this differential equation, somewhat of a quasi-order dimensional differential equation. Augustin Cauchy and Leonardo Euler, Cauchy French and Euler, Swiss mathematician, worked independently, and they did not come up with this differential equation. They came up with solutions, of which we'll deal with today, and I'll go over some of the proofs of how Euler in particular came up with it, and Cauchy, his work is on the second type. Euler's work is on the third type that we'll talk about today. So we solve this differential equation, this this nth order differential equation that we call the Cauchy Euler. And what we're going to find out is that there are three possibilities in the solutions. Very similarly, back in chapter 4, when we had the second order differential equation of constant coefficients, and we had three solution types, if you recall. We had distinct roots, we had repeated roots, and we also had complex roots. Well, here the model was set for us in chapter 4, so we'll use that model here. In this problem, it will work itself, if you will, and you'll see that you will run across some quadratic roots for the auxiliary equation, and from that you deduce that you have distinct roots, repeated roots, and complex roots. If the differential equation is non-homogeneous, then we'll solve the non-homogeneous differential equation. That is that you have a g of x over here that's not equal to 0. We'll solve that using variation of parameters, and that was the previous section that we came out of. Okay. Today we consider only the second order differential equation for the Cauchy Euler. Why the second order? Because most things in nature tend to hover here, whether it's fluid flow, temperature, heat, motion, all of those things are confined here with the second order differential equation. So we spend our time there. I remember when I took partial differential equations, we dealt with a second order differential equation, only one equation, only one second order partial differential equation for the entire semester. We only worked to solve one problem. Wow, very difficult. So here for this statement for equation number 1 is the same thing as the previous equation with the nth order, but here for equation number 1, we simply say let n equal to 2. So you have the nth order. Well, what if n is equal to 2? So you have the second order differential equation. So to understand the form of the solutions to the Cauchy Euler equation, consider the first case. Consider if n is equal to 1. Remember that day last week that I kind of got off and I was doing something and I said, don't worry about it? Well, I was thinking about this right here. So if n is equal to 1, we're talking about this n for the nth order, then what we have here is if n is 1, then I don't have any second order, third order, so we have then b times x times dy over dx plus c times y is equal to 0. Now I'm going to clean that up. Instead of having b and c, I'm going to put a and b. Okay. So that is, we can write this as ax times dy over dx plus b times y is equal to 0. Letters are dummies and not humans, so we do not call humans dummies, but if you call a letter a dummy, it's okay. Now, when that letter starts to talk back, then you change your major, right? So I'm going to solve this guy simply by separation of variables. So when we do that, we have ax times dy is equal to negative b times y times dx. Divide both sides by x, divide both sides by ax, and divide both sides by y. And so we have 1 over y times dy is equal to negative b over a times x times dx. Integrating both sides. So it gives us the natural log of y, absolute value by all means, is equal to negative b over a times the natural log of x plus, let's say, c sub 1. And if we add the b over a natural log of x to both sides, so this implies that we have the natural log of absolute value of y plus the natural log of x raised to the b over a is equal to this c sub 1. Well, this implies that we have the natural log of y times x, where x is raised to the b over a, is equal to c sub 1. Exponentiate both sides, and so we get e to the natural log of y times x raised to the b over a is equal to e to the c sub 1. And that implies that we have y times x, and x is raised to the b over a is equal to, let's call this e to the c sub 1c. This implies that a solution for the first order differential equation, for the Cauchy Euler differential equation, is y is equal to c times x to the negative b over a. Now, if you let m equal to negative b over a, so this implies that y is equal to c times x to the m. So we take the solution to be of the form y equal to x to the m for n equal to 1 and n greater than or equal to 1. So here's the point. If we have a Cauchy Euler differential equation, what is that? A differential equation of this form here, and ideally for today we deal with the second order Cauchy Euler, so we primarily focus on equation number 1. If we have a differential equation of this form, what is that form? That when I have the differential equation, if I have a derivative in the differential equation, then associated with that derivative is an x term, and the power of x is going to be the same as the number of the order for that derivative. Right? So x to the second derivative. X to the first derivative. No x, no derivative. If that be the case, then the solution will be of the form some y equal to x to the m. What we mean is that the solutions here are polynomial in form. If it's a differential equation with constant coefficients, then the solution, we said, was exponential in form. That was back in chapter 4. Right? So we had c sub 1 times e to the mx plus c sub 2 times e to the some other form of mx. Well, we said e to the m sub 1x and then e to the m sub 2x. But here, the solutions of this form, x to the m. polynomial. Now we have auxiliary equations given here, but that doesn't mean anything until we can show how we get that. So how do they get these equations here that they call number 2? Let's see. So here, consider a times x squared times y double prime plus bx times y prime plus c times y is equal to 0. This is equation number 1. Since we make the assumption from the first order that the solution is of the type y equal to x to the m, then we assume that here. So assume solution type is y equal to x to the m. Well, for this equation number 1, we have y, we have y prime, we have y double prime. So let's go ahead and solve for y prime here. That's going to be m times x to the m minus 1. And y double prime is equal to m times m minus 1 times x to the m minus 2. Are you with me? Okay. So we're going to substitute back into equation number 1 for y prime, and y double prime of this polynomial form. So we say this implies then that we have a times x squared times m minus 1 times x to the m minus 2 plus b times x times m times x to the m minus 1 plus c times x to the m is equal to 0. Now what I notice here, a couple of things. Do you see that x squared would cancel out with this x to the negative 2? And that x to the first would cancel out with x to the negative 1? Do you see that? Okay. Somebody don't see it. It's okay. So this is ax squared times m minus 1 times x to the m times x to the negative 2. Now do you see that? Are we friends again? Well, maybe not, but okay. Times m times x to the m times x to the negative 1 plus c times x to the m equal to 0. Now you see that some terms cancel out. This x squared cancels out with x to the negative 2. X to the first cancels out with x to the negative 1. So what we have left now is a times m minus 1 times x to the m plus b times m times x to the m plus c times x to the m is equal to 0. There's a common term of x to the m. We factor that x to the m out, and so we have x to the m times brackets a times m minus 1 plus b times m plus c equal to 0. Now, to ensure that we have a solution of the form that is polynomial form, we assume that the solution is on the interval, open interval from 0 to positive infinity. If you don't have that, then we have one point, we get into some trouble. So if we assume that, then we're fine. So here, assume that the solution for equation 2 are all on the interval from 0 to positive infinity. You can assume that the solutions will be on the interval from negative infinity to 0, open, or from 0 to positive infinity. If you're dealing with real-term situations, then it might not be to your advantage to assume that the solution will be on the interval from negative infinity to 0. But it would be to our advantage to assume that the solutions would be on the interval from 0 to positive infinity. Here's the hiccup. We're basically assuming that the key is that the solution is not 0. Because if it is 0, then we get some trouble. Now, if it happens to be 0 in just a real sense, then that's fine. But for the order of the algebra to work, that here we assume that the solution is on the interval, open interval from 0 to positive infinity. The key or the hiccup is at 0 itself. And this is at the point that we have a hiccup. Here's the hiccup. You see this equation right here, x to the m times the brackets is equal to 0. So we say here that either x to the m is equal to 0 or what's inside the bracket is equal to 0. It's like one or the other. So if you kick out that you can't have a 0 solution, then x to the m is not equal to 0. Right? So here we have x to the m equal to 0 or a times m minus 1 plus b times m plus c equal to 0. Since the solution is on this interval, then x to the m is not equal to 0. Thus, we have a times m minus 1 plus bm plus c is equal to 0. Now you can fix that up, or if you multiply everything out, this is am squared minus am plus bm plus c equal to 0. That is, we have am squared plus parentheses b minus a times m plus c equal to 0. These two, what's in red and what's in green, captured there, they're the same. We call this the auxiliary equation. This is equation number 2. Well, that's where the auxiliary equation comes from. We call this the auxiliary equation. Now let me ask you a question. The auxiliary equation, what form is it? It's a what kind of equation? It's quadratic, right? It's quadratic. And if it's quadratic, then we know that there are three types of solutions for the quadratic. Either we have distinct roots, repeated roots, or complex roots. Okay? So we follow the same paradigm as before. The solution is a little bit different in how we write them. So here we note the solution types here are in three forms. So here there are three solution types for Cauchy Euler equation. Distinct roots, number 2. Repeated, and number 3, complex. So the first type is that if we have the solution type to be distinct, let's see how that looks. So case number 1, distinct roots. Let m sub 1 and m sub 2 be the roots that are different that we get. And so the solution in terms of how you write it is y equal to c sub 1 times x to the m sub 1 plus c sub 2 times x to the m sub 2. Now, that equation number 3 that we got numbered here, what tells us that we can write our solutions of that form? Why do you put the c sub 1 times the first solution plus c sub 2 times the second solution? Why is that? Okay, but why can I write, and why do I write the solution of this form? Because of the superposition principle. Huh? Right? Isn't that the superposition principle? Right? This we call the complementary solution for the superposition principle. And so the point that I'm trying to make is that everything that we do in this course, there has to be a reason. That there must be justification. Just don't do what I want to do. Well, you can, but it's not good. Right? So, number 1, let's solve. Yeah. All right. So here's the method that you're going to use, and I'm going to give it to you. So you start by saying let y equal to x to the m. So we take the derivative y prime. We just follow the steps of the order that I just got through doing in the previous page. Y prime is m times x to the m minus 1. And y double prime is m times m minus 1 times x to the m minus 2. So I take the problem. I'm going to just rewrite the y's and the y prime and the y double prime. So this is x squared times y double prime. That's m times m minus 1 times x to the m minus 2. Minus 2 times x to the m, that's equal to 0. Now, you understand that the x to the second and the x to the minus 2 cancels out, right? Right? Only one person shook their head and said yes. Okay, thank you. Good. So this is now m times expression m minus 1 times x to the m minus 2 times x to the m equal to 0. Factor out x to the m. We have left m times m minus 1 minus 2. That's equal to 0. We said that the solution is on the interval from 0 to infinity, open at 0, so that does not include x to the m, or x to the m cannot equal to 0. So this implies then that m times m minus 1 minus 2 is equal to 0. That is, we simplify that. This is m squared minus m minus 2. We can factor that. This is m minus 2 times m plus 1 equal to 0. So we get m equal to 2, and m is equal to negative 1. So by the superposition principle, the complementary solution is y is equal to c sub 1 times x to the second plus c sub 2 times x to the negative 1. Okay. Any questions there? All right, the second type. When you have repeated roots, and the roots are real, if there's complex roots, then we deal with that for case number 3. So here the solution type is written c sub 1 times x to the m sub 1 plus c sub 2 times x to the m sub 1 times the natural log of x. The question here is, why the natural log of x, right? Fiaja, where does the natural log of x come from? We don't know, right? We don't know. So we have to show and to prove that this is what we call in mathematics something that's well defined, that is provable, is well defined. Let's see. So all we know is that from the repeated roots that m sub 1 is the same as m sub 2. I get the same thing. So what we're dealing with is this a times m squared plus b minus a times m plus c is equal to 0. This was the auxiliary equation. And what we're saying is that this value for m, we're getting m sub 1 is equal to m sub 2. So y sub 1 we know is x to the, I'm just going to say m, x to the m instead of m sub 1. We know that. We find the second solution by the formula. Y sub 2, you remember, is equal to y sub 1 times the integral of e to the negative integral of p of x dx divided by y sub 1 to be squared dx. Okay? That's the formula, right? So what is p of x? No. This is an auxiliary equation. This has nothing to do with the differential equation. I mean, it does, but it's indirect. Right? You're saying it's x. Let's go back and look at it. Let's go back and look at it. Right? Given ax squared times y double prime plus bx times y prime plus c times y is equal to 0. Now my question is, what is p of x? Because look, you got to have y double prime plus p of x times y prime plus q of x times y is equal to 0. So my question is, what is p of x? B over ax. Do you see that? Because how do you get the p of x? You have to divide everything by the coefficient of y double prime. Right? So this implies here that we have y double prime. You got to be careful for that. This is bx divided by ax squared times y prime plus c over ax squared times y is equal to 0. So p of x is equal to b over ax. Okay. Now, in the auxiliary equation, go back to that. You know, you have am squared plus b minus a times m plus c equal to 0. M is equal to negative parentheses b minus a over 2a for repeated roots. How did I get that? Let's see if I can clarify it. That is, m is equal to negative b minus a plus or minus the square root of b minus a to be squared minus 4 times a times c all over 2a. But if it's repeated roots, the discriminant is equal to 0, right? The radical is 0. So all you have left is negative parentheses b over b minus a divided by 2a. Or you could just say this is a minus b over 2a. So y sub 2 is equal to x to the m times the integral of e to the negative integral of p of x. P of x is b over 2a, b over ax, b over ax dx, and that's divided by x to the m to the second, or x to the 2m dx. So this is x to the m times the integral of e to the, we integrate this term up here, so this is negative b over a times the natural log of x. That's all over x to the 2m dx. So y sub 2 is equal to x to the m times the integral of, this is x to the negative b over a all over x to the 2m dx. All right, are you with me there? Okay. So we simplify this. We're just going to bring this x to the 2m upstairs. This is x to the m times the integral of x to the negative b over a times x to the negative 2m dx. But we said here that m is equal to a minus b over 2a. So y sub 2 is equal to x to the m times the integral of x to the negative b over a, that's minus 2 times m, and m is a minus b all over 2a. It's dx. Simplify that if we can. This is x to the m times the integral of x to the negative b over a. The 2's cancel out. This is minus, see the 2's cancel out. This is minus a over a. Minus, and the minus is plus. We got rid of the 2, so this is plus b over a dx. The minus b over a and the plus b over a would cancel out. So we have y sub 2 is equal to x to the m times the integral of x to the negative 1 dx, right? Because a divided by a is just 1, so it's x to the negative 1, which is just 1 over x. So this is x to the m times the natural log of x. Right? So we take y sub 2 to equal to x to the m times the natural log of x. And so y sub c is c sub 1 times x to the m for repeated roots, right? Plus c sub 2 times x to the m times the natural log of x. If the differential equation here, the Cauchy Euler equation, was of the third order, like the third derivative, and if you had 3 repeating roots, then it'll be plus c sub 3 times x to the m times the natural log of x to be squared. Right? You just keep going in that fashion. Very similarly, you remember back in chapter 4 where you had the differential equation with constant coefficients. If it was repeated roots, you know, the first term would be is c sub 1 times e to the mx plus c sub 2 times x, right, times e to the mx. If it repeats again, then it's c sub 3 times x squared, right? You keep on going up, times e to the mx. Same thing here, but instead of x, the repeat here is on the natural log of x. Right? Now let's look at a problem where we make use of this. Numbers 3 and 11. Let's do number 11, and then you can do the other one as part of the homework anyway. So we start off with these. Let y equal to, x to the m. Y prime is equal to m times x to the m minus 1, y double prime m times m minus 1 times x to the m minus 2. So for the problem, we have x squared times y double prime, so that's m times m minus 1 times x to the m minus 2 plus 5 times x times m times x to the m minus 1 plus 4 times x to the m is equal to 0. The x squared will cancel out with x to the negative 2. X to the first cancels out with x to the negative 1. So we have here, and if you will, I want to just go ahead and just factor out the x to the m at the same time too. So this is x to the m taken out. So I have m times m minus 1 plus 5m plus 4 is equal to 0. This implies that just inside the brackets, simplify that, that's m squared minus m plus 5m plus 4 equal to 0. So this gives us m squared plus 4m plus 4, and we can factor that. This is m plus 2 times m plus 2 equal to 0. So m equals to negative 2 twice. So if that be the case, then y sub c is c sub 1 times x to the negative 2 plus c sub 2 times x to the negative 2 times the natural log of x. Any questions? Okay. That last part, I got 2 more problems to do. Case number 3, and then I need to solve one using variation of parameters. So, and that last problem takes like 20 minutes. So, but anyway, case number 3. What happens when for the auxiliary equation, the roots are complex? How do we get this? Well, let's see. So here, let m equal to alpha plus or minus beta I. And you recall Euler's formula. E to the I times theta is equal to cosine theta plus I times sine theta. So we use that. So we have y is equal to, or y sub c if you will, is equal to c sub 1 times x to the alpha plus beta I plus c sub 2 times x to the alpha minus beta I. And what's common in both would be the x to the alpha, so we factor out x to the alpha. We have left in brackets c sub 1 times x to the beta I plus c sub 2 times x to the negative beta I. Okay. There's a problem. The problem is that Euler's formula says that you can convert from transcendental to transcendental. That is, you can go from E-base function to sine cosine and vice versa. It does not say anything about going from polynomial values of x to some transcendental form of either E-base or sine and cosine, right? Just Euler's formula here, it says E base, right, can be converted to some cosine, some sine combination. Here we have our base is x, it's not e. It's totally different. So we manipulate it. We just use our algebra and manipulate it. Here's what we do. What if you have this? If we have e to the natural log of x to the beta I. Isn't that the same as x to the beta I? Right? So we have the e base there, if you will. We'll go back to this form here. So this is e with the natural log of x. If I have an exponent here, can't you write the exponent as a multiple of the natural log? So we're going to write this as e to the bi times the natural log of x. And to write it in the form here of e to the I times some angle, I'm going to say this is e to the I times beta natural log of x. So you can kind of almost get the flow of how in equation number 5, see how they have the cosine beta natural log of x? You can kind of see, where it's coming from. So I'm going to make the replacement, because notice this, that this is the same thing according to Euler's formula. This is cosine beta natural log of x plus I sine beta natural log of x. I got my old professor in my head. I've said to you all to listen to what I'm saying, because when I was in class, I was listening to what he was saying as well, and so I'm repeating what he's been saying. And he was a funny old guy. He just died a few months ago, Dr. Maryland, and he wouldn't say beta, he would say beta, and maybe he said that just to be funny, but I don't know. Still got the old man in my head. So if that be the case, then we go back, y sub c, it doesn't look pretty. Y sub c is equal to, we had factored out x to the alpha times, so c sub 1, x to the beta I becomes, let's put that in parentheses, cosine beta natural log of x plus I sine beta natural log of x. Close that one up. Now plus c sub 2. This is x to the negative beta I. So here where I have beta natural log of x, we just put a negative there. This is parentheses cosine of negative beta natural log of x plus I sine negative beta natural log of x. Close this parentheses, close that parentheses, and then close the brackets. Now the cosine of a negative translation is the positive translation, and then a sine of a negative translation is the negation of that particular translation. So here this is y sub c is equal to x to the alpha times the brackets c sub 1 parentheses cosine beta natural log of x plus I sine beta natural log of x. This is plus c sub 2 times cosine beta natural log of x, and this becomes negative I sine beta natural log of x. And parentheses here, parentheses there, close that up. Now I'm going to get the like terms together. I'm going to get the cosines together and we get the sines together. So y sub c is equal to x to the alpha times, and getting the cosines together, this would be, I'm sorry. Is it still raining? A little bit. Put a hat on these C's. It's raining. I forgot to put the hat on. It's raining. I forgot to put the hat on. Okay. So this is, yes, C sub 1 hat plus C sub 2 hat times cosine beta natural log of x. Plus, get the signs together. This would be parentheses C sub 1 hat times I, and then minus C sub 2 hat I. This is times sine of beta natural log of x. So now let's say let C sub 1 equal to C sub 1 hat plus C sub 2 hat, and C sub 2 is equal to C sub 1 hat I minus C sub 2 hat I. And so this implies that the solution for the complex conjugate for the complementary solution is x to the alpha times C sub 1 times cosine beta natural log of x plus C sub 2 sine beta natural log of x. Now you know how the solution is derived. Don't you feel a whole lot better? Don't answer. Now let's look at a problem and where we make use of this formula. Number 5. So I think you kind of get it. If it's y double prime, it's m times m minus 1 times x to the m minus 2, right? If it's y prime, it's m times x to the m minus 1. So this is m times m minus 1 times x to the m minus 2 plus x times m times x to the m minus 1, excuse me, plus 4 times x to the m. And so what we have, and we say this implies that we have m times m minus 1 plus m plus 4 equal to 0. Are you with me? Lauren, are you with me? Okay. So this is m squared minus m plus m, oops, jumping the gun, plus m plus 4 equal to 0. We get m squared plus 4 equal to 0. That implies that m is equal to plus or minus 2i. So alpha is 0 and beta is equal to 2. So we go by the formula. So y sub c is c sub 1 times cosine 2 natural log of x plus c sub 2 times sine of 2 natural log of x. So there is no x really to the alpha. I mean, it is, but alpha is 0, so x to the 0 is 1. Okay. Any questions there? So then, the last type is to, if you have a Cauchy Euler non-homogeneous differential equation, what do you do? So let's look at this problem here. I wanted to do that problem, but the time is of essence, and I won't be able to finish it in 10 minutes. So I think I can finish this guy in 10 minutes. So we solve this in two parts because it's non-homogeneous. So we first solve x times y double prime plus y prime equal to 0. Is it Cauchy Euler? Yes, it is. You say, well, if it's y double prime, how come we don't see x squared? And if it's y prime, how come I don't see an x multiplied to it? Really, it is there. They just factored it out. Right? So if you think about that as being x squared y double prime plus x times y prime equal to 0. And if you factor out, divide out an x, so this implies that you have x times y double prime plus y prime equal to 0. So really it was there. So if it's y double prime, then we're going to write in its place m times m minus 1 times x to the m minus 2. So this is x times m minus 1 times x to the m minus 2 plus y prime is m times x to the m minus 1 is equal to 0. So what we have here, this x to the first will cancel out with one of the x's to the negative, x to the negative 1. So I have left m times m minus 1 times x to the m minus 1 plus m times x to the m minus 1 equal to 0. Factor out x to the m minus 1. I have left m times m minus 1 plus m equal to 0. So x to the m minus 1 cannot equal to 0. So this implies that the m times m minus 1 plus m is equal to 0. So simplify that auxiliary equation. So we get m squared minus m plus m equals 0. This implies that m squared is equal to 0. That is, m is equal to 0 and m is equal to 0. So for the first part, y sub c is equal to c sub 1 times x to the 0 plus c sub 2 times x to the 0 times the natural log of x. You can simplify that. That is, we have c sub 1 plus c sub 2 times the natural log of x. So step number 2 for the variation parameter method, bless you, y sub 1 is 1, right? And y sub 2 is the natural log of x. So we solve x y double prime plus y prime is equal to x. I think that was the original problem. Yes. Okay. To simplify that, this is y double prime plus 1 over x times y prime is equal to 1. Now, why did I do that? I'll show you in just a minute. So the two equations that we want is the 1, which is y sub 1 times u sub 1 prime plus y sub 2, which is the natural log of x, times u sub 2 prime is equal to 0. And the next thing you do is take the derivative of y sub 1, so that's 0 times u sub 1 prime, plus the derivative of the natural log of x, which is 1 over x, times u sub 2 prime is equal to what for the variation parameters? Is equal to f of x, right? What is f of x? What is f of x? F of x is equal to 1. If you have ax squared times y double prime plus bx times y prime plus cy is equal to g of x, this is the non-homogeneous second order Cauchy Euler equation, right? Well, you convert that into the proper form, that is by dividing through by ax squared. So you get y double prime plus, we said here, p of x times y prime plus q of x times y is equal to what? F of x. So what's f of x? How do you get f of x? No. It's g of x divided by ax squared. Notice here, you've divided everything through by ax squared, right? To get this form. So px is bx divided by ax squared. Qx is c divided by ax squared. F of x is gx divided by ax squared. So the original problem was x times y double prime plus y prime equal to x. Well, the x over there is the g of x, right? And the ax squared here is that x. So x divided by x is 1. 1 is f of x. See that? Told y'all to watch out for that. So this guy right here, that's what we're saying. Right? This is y double prime plus p of x times y prime is equal to f of x. For this problem here, there's no q of x. Q of x is 0. So the Warren scheme for W, go back and look at the system, is 1, 0, natural log of x, and 1 over x. So 1 times 1 over x is 1 over x, minus 0 times natural log of x, so it's just 1 over x. W sub 1, replace the first column with 0, 1. So this is 0, 1, and then this is the natural log of x. This is 1 over x. So we get 0 minus the natural log of x. W sub 2 is 1, 0, and replace the second column with 0, 1. So we get the identity matrix, so that's just 1. So we said u sub 1 prime is equal to w sub 1 divided by w. So this is negative natural log of x all over 1 over x, or just negative x natural log of x. And u sub 2 prime is w sub 2 divided by w, and w sub 2 is 1 all over 1 over x we just get x. Now, let's come here. Let me get the u sub 2 first. It's easy to get that guy. So this is the integral of u sub 2 prime dx. So this is the integral of x dx, which is 1/2 x squared. That's all we need for that one. U sub 1 is the integral of u sub 1 prime dx. So this is negative integral of x, natural log of x dx. Takes a little time to get to that one. Let's see if I can jump ahead. Bless you. Recall that the integral of the natural log of x dx is x times the natural log of x minus x. We get that by integration by parts. I don't have time to, that's calculus 2. Right? I'm already past the time by 1 minute. So integration by parts. But that still doesn't help us because this is the integral of x times the natural log of x. So I use the tabular method. X, 1, 0, positive, negative, positive. And then here, this is the natural log of x. And its integral is x, natural log of x minus x. I don't want that method. This is the integral of x, natural log of x dx. I have to use just the old-fashioned integration by parts. So let u equal to x and dv is the natural log of x dx. So du is equal to dx, and v is equal to this guy right here, x, natural log of x minus x. This guy has, if you recall, there were certain problems in calculus 2 that had a recursive, like it kept repeating, and so this is what this guy is going to do. So that tabular method doesn't help us out so well. So u sub 1 is equal to negative, this is going to be u times v, so x squared natural log of x minus x squared minus the integral of v du, so minus x natural log of x minus x dx. So this guy is equal to negative x squared natural log of x plus x squared plus the integral of x natural log of x dx. See, this is negative, negative. This is plus. Well, it's another negative there. So 3 negatives, negative, negative, negative. So this is minus the integral of x dx. Let's integrate that right there because it's not giving me any space down below. So just integrate this guy. So that's just 1/2 x squared. So now, this guy becomes, this u sub 1 is this guy right here. So this guy is, this is negative the integral of x times the natural log of x dx is equal to I lost the negative somewhere. Because to get this guy back on the other side, it's going to cancel that. No, I didn't. I'm fine. All is well. All is well. Let me finish this problem, because this problem will make me sick, for a couple of days if I don't finish it. So, excuse me. This is dx. I'm going to take this guy and subtract it on both sides. This is minus the integral of x, natural log of x dx. That's equal to this part and this guy right here. So this is negative x squared natural log of x plus x squared minus 1/2 x squared. So that's just plus 1/2 x squared. So this is minus 2. Where's my other page to add? I think that's it. So this is minus 2 times the integral of x, the natural log of x, dx is equal to x, negative x squared, natural log of x plus that guy right there. Good. Negative x squared, natural log of x plus 1/2 x squared. Divide by 2, so this u sub 1 is negative the integral of x, natural log of x dx is equal to negative 1/2 x squared, natural log of x plus 1/4 x squared. Okay, so that was u sub 1. What was u sub 2? Do you recall? Was it just 1/2 x squared? 1/2 x squared. Good. So y sub p is y sub 1 times u sub 1 plus y sub 2 times u sub 2. And I think we had y sub 1 was 1, and y sub 2 was natural log of x. So y sub p is equal to 1 times all of this for u sub 1, negative 1/2 x squared, natural log of x plus 1/4 x squared, and then plus the natural log of x, and then u sub 2 is the 1/2 x squared. Okay, do you see what's going to happen? This is negative 1/2 x squared, natural log of x plus 1/4 x squared, and this is plus 1/2 x squared, natural log of x. It kind of burns me up a little bit, but it's okay because it kind of suggests that maybe you did something right. Well, see these two terms right here cancel out, and so you say you did all that work and they cancel out, But then at the same time, well, maybe you did something right. Well, not necessarily. So then the final answer, we don't like red. It's hard to see. So this is c sub 1 plus c sub 2 times the natural log of x plus y sub p, which is just plus the 1/4 x squared. I thought the other problem was going to be longer. But anyway, when you go into Blackboard, you'll see my announcement of how this test is going to look. Watch my lecture on 5.1. Going to have a couple problems from 5.1 on the exam. They're very straightforward. If you have questions, by all means, email me. I will be out of town this week, but I'll be back next week. Even though you won't be here next week, I'll be around. So if you want to email me some questions, whatever, that'll be fine. And then when you come back on the following week after spring break, that test 3 will be available in the testing center for Monday and Tuesday. Okay? Thank you.